Hello, you're welcome back. All right, so now in this video we are looking at DC current circuit. Okay, so the DC here actually is the abbreviation for direct current circuit. Now, as you already know, okay, a direct current is actually a current that is steady, a current that is steady throughout the time interval. Now, the opposite of DC current is alternating current. Okay, so invariably the current that actually comes from battery, okay, or a cell is actually a direct current, because the current doesn't change. Okay, it's steady for um, the particular period of time that this particular the battery or the cell is supplying the current to the external circuit. So now we're going to be looking at direct current circuit, and in this particular uh, tutorial we'll concentrate on the resistor circuit. Okay, that is circuit that is just made up of resistor. So I believe that you know what a circuit is. A circuit is actually a closed path, okay, through which current flows from a source. Okay, and here these are some electrical symbols that we are going to be using. So this is a symbol for a cell, right, and this is a symbol for a resistor. This is also a resistor. Okay, a fixed resistor symbol. Then this is a symbol for a battery. A battery is made up of more than one cells, as you can see. All right. Then this is a symbol for a key or a switch. Whenever you open the switch, the current will not flow. When you close it, current flows. So this is a symbol for ammeter, used for measuring direct current. Okay. This is a symbol for voltmeter, used in measuring voltage. All right. So let's start with our circuit analysis. So we're going to be looking at a circuit that is made up of resistor. Now, the circuit that is made up of resistor has different connection, and basically two types of connection. Will have parallel and series connection. So I'll start with resistors in series. I'll start with resistors in series. Okay. So now, this is a typical connection of resistors in series. Now, these resistors are said to be in series. Why? Because the same piece of wire is connecting all of them. All right, then that wire now connect them to a voltage source. Okay, so this is a typical example of resistors in series. So let's have this resistor R1, R2, and of course R3 in series, connected to a voltage source V. All right, so now this voltage source actually delivers current to this resistor, and for the fact that these resistors are connected in series, okay, the same current flows through them, but the voltage across each of the resistor varies. So the voltage across R1, I call it V1. Okay, voltage across R2, I call it V2, and voltage across R3, I call it V3. So that means the entire voltage, okay, the total voltage that is supplied to these three resistors, they share it among themselves. Okay, V1 plus V2, then plus V3. Okay, so this voltage, this total voltage V, let me call it V, is shared among these resistors in this manner, right? So from Ohm's law, by now I believe that you know Ohm's law. Okay, from Ohm's law we have this formula that V is equal to IR. Okay, potential difference is always equal to current times resist. So potential difference is always equal to current times resistance. So I have to replace that into this expression. So total Vt is going to be equal to V1. Okay, of course for Vt, that's going to be IRT. And don't forget that current is the same, okay? So I will be the same throughout. So that's going to be for V total, that's going to be IR total. For V1, that's going to be IR1. For V2, that's going to be IR2. Then for V3 now, that's going to be IR3. Okay, now looking at the right hand side of the equation, you discover that I is actually common. I is common, okay? So that's why I have to factorize. So since I is common, I factorize. I have I is placed outside the brackets. I have R1, R2, and of course R3. Okay. So since I is a common factor at both sides of the equation, I can just take it out. So I now have that the total resistance for series connection is gotten by adding the individual resistance R1 plus R2 plus R3. Okay. So now when resistors are connected in series, for you to find the equivalent resistance or total resistance, you add up. For example, if what I have here is 2 ohm, 2 ohm, 2 ohm, then the total resistance I will get in this series connection is going to be equal to 2 plus 2, okay, plus 2, that's going to be 6 ohm. So I hope that is well understood. Okay, so now we are done with resistors in series. So let's look at resistors in parallel. Resistors in parallel. Okay, now this is how the parallel connection, okay, will be like. Now I'll tell you what makes it parallel connection. When we discuss capacitor, I've already told you, okay, why I will say that components are connected in parallel. Components are connected in parallel if only if there's a branch, okay, that current actually divides among the components. So if you look at this now, okay, this is 3 resistors connected in parallel, then across a voltage source, okay, current flowing through these 3 resistors will definitely branch. So the main current, which is the parallel connection, that you now discover there's a branch. So anytime you go through the path of current and you discover a branch, it simply means that this what you have is parallel connection. So let me call the first resistor there R1, okay, the second one is R2, and the third one is R3. So that means current will divide. The one that will enter R1, let me call it I1. So current I1 enters R1, current I2 enters R2, and current I3. So the current will definitely divide. But meanwhile, the voltage is the same. Okay, parallel connection, all this R1, R2, R3, they'll have the same voltage. And that voltage that they will have is going to be equal to the supply voltage, okay? But what varies is the current. So since the current varies, so I will say now say that, okay, the total current, okay, because it is the total current that actually enters into this branch to divide into I1, I2, and I3. So total current is going to be equal to I1 plus I2, then plus I3. So still from Ohm's law, okay, we know that V is equal to IR by 12. So if I make I the subject of formula, I will now going to be equal to V all over R. So substituting into this equation, so for IT, the total I, so that's going to be V, that's going to be V all over RT. For I1, that's going to be V all over R1. For I2, that's going to be V all over R2. for I3, that's going to be V all over R3. Okay, so V is common, it's the same. So now I've got to factorize the V since it's a common factor. So I'll take the V out. Okay, so the factor that's left is going to be 1 all over R1, then plus 1 all over R2, then plus 1 all over R3. Okay, so of course, since V is a common factor both sides of the equation, it will cancel out. So I'm left with 1 all over R total is going to be equal to 1 all over R1 plus 1 all over R2, then plus 1 over R3. So invariably now, so if you are being asked to find the total or equivalent resistance when resistors are connected in parallel, you sum their reciprocal, as you can see. So let's say the resistors are just 2, 2, 2, 2, okay, like before. Then they are 1 all over the total resistance, 1 over RT will be 1 all over 2 plus 1 all over 2, then plus 1 over 2. So when the LCM here is 2, 2 divided by 2 is 1, 1 times 1 is 1. 2 divided by 2 is 1, 1 times 1 is 1. 2 divided by 2 is 1, 1 times 1 is 1. So 1 all over RT is equal to, of course, 3 all over 2. So for me to find RT, I have to inverse. Okay, I have to invert the reciprocal. That's going to be 2 all over 3. Okay. Oh, all right. I hope that is well understood. But there's one thing: it's just very easy for you to be given parallel connection, just parallel connection, to resolve the total resistance. It's easy for you. You can do that easily, and it's also, you can do that easily for a series resistor. But in most times, the question they ask you in examination is complex. Okay, it's a combination of series and parallel. Okay, so they ask you to resolve a combination of series and parallel. So let's look at some example. Okay, the question is evaluate the equivalent resistance below. Okay, so now I'll be drawing some circuits, then we are going to be solving different circuit, okay, questions. So see you in the next video.